Alright, welcome to lesson 11.4. Today we are going to talk about bivariate data analysis. Specifically, your aim is that you can analyze data involving two variables by creating a line of best fit and a scatter plot and describing correlation. I'm going to teach you what correlation is later on in the lesson. Oftentimes, statistical studies are done where data is collected on two variables instead of one in order to establish whether there's a relationship between the two things. This is called bivariate data analysis. So exercise 1 is going to walk us through how to create a scatter plot and think about correlation. So exercise 1 says, a survey was taken of 10 high and low temperatures in Fahrenheit in the month of April to try and establish a relationship between the day's low temperature and the high temperature. So we're looking at two different variables, low temperature and high temperatures, and we want to see if there's a relationship. So A says, first construct a scatter plot of this data below. So it tells us that low temperatures are X and high temperatures are Y. So I look down here on my low temperature and high temperature, and I'm going to label these a little easier. I can see that it's going up by 2, so this is 22, this is 24, 26, 28, and I'm just going to finish labeling this. It's going to help me see my points a lot easier. I'm going to label the side as well. It's also going up by 2s, 52, 54, 56, 58, and 72, 74. Okay, so I've labeled my grid a little easier so I can see it. And now A says construct a scatter plot of this data. So I'm looking here, these right here are points, an X and a Y coordinate. So this is like saying the coordinate 26, 49. So I'm going to graph 26, 49. 26 is here, 49 is right here in between. If I label this over here, this would be 48 and this would be 46. So 49 is halfway between. And I'm just going to keep plotting these points. This next one is 28, 30. So I'm going to plot 28, 2850. 2850. Make another point here. And I'm going to keep going through these points until I plot each of them on my grid. 3057, it's right here. 3254, so I'm just going to check these off when I do them. So 3254 is right here. 3460, 34 and 60 is right here. 3558, so 35 is halfway between here. So 35 and 58, so right there. 3764, 37 is in between here, and 64 is all the way up here, so there's 3764. 3866 is my next one, so I'm going to go to 38, and then I'm going to go up all the way to 66. And then finally, last two, 4163. 4163 is right here. It's like right in the middle. It's kind of a tough point. And 4572 is all the way up here. Okay, so now I've constructed this, and this is called a scatter plot. Okay, because all of the points seem very scattered. Okay, so this is a scatter plot, not scattered, but scatter plot. Okay, all the points are kind of scattered around. So that's letter A. I've constructed my scatter plot. The next thing we're going to do is something called a line of best fit. I don't know if you've done this in middle school, but a line of best fit is kind of what it sounds like. You're trying to make a best fit out of the points possible, and a line is straight. So what I'm going to do is I'm going to kind of just draw an estimate of what my line is going to look like between this first and this last point. So I'm going to make my line, and it kind of looks like this. Right? It's kind of going through some of the points, not all, but this is my best fit line. There's no one perfect way to do this. You're estimating your line of best fit. You're just kind of drawing a line through these points. Okay? So that was line of best fit. Now the next part says calculate your slope by picking off 2 points, not necessarily data points. So I'm going to look at my line of best fit, and I see that my point kind of goes through here, and my point goes through here. So I've got these 2 points in blue, and I'm going to use that to make my slope. Now remember, slope formula is y2 minus y1 over x2 minus x1. This first point right here is 42, 70, and this other point right here is 36, 60. So there's my x1, y1, and my x2, y2. So my formula, well, here are my 2 points. I'll write them a little nicer. 42, 70, and I have, and the point 36, 60. So these are the 2 points that I drew on my line of best fit, and I'm going to calculate the slope. So I'm going to have 70 minus 60 over 36 minus 42. Okay, now, like I said, you could have picked any points you wanted. I just picked 2 that were close, that fit through the graph. There's no one right way to do this. And on the exam, you know, one student could pick 2 points here, but another could pick 2 different points. Your slope should still be about the same, because a line, all the slope is the same. So 70 minus 60 is 10, and 36 minus 42 is 8. 10 divided by 8 becomes 5 over 4, which gives me 1.2 as my slope. So my slope is 1.2, okay? That's like basically your M, right? 1.2 is your M of your line of best fit, okay? Now, this is useful. Why am I doing this? Why am I doing any of this? Because now this next question is asking me to predict something. Use your line of best fit to estimate the high temperature for a day in April, given the low temperature was 42. So now we're estimating and we're predicting. So based on previous data, we're going to estimate future data. Okay, so I'm going to go to my graph and I'm going to look at 42 degrees, which is right here. So here's 42 on my graph, and I'm going to estimate, well, where does that hit on my line? It hits it right about there, and that's a little bit above 67 degrees. So I can put as my estimate, well, I estimate around 67 degrees Fahrenheit. Okay, that's my estimate. So on the day in April, given the low temperature is 42, the high temperature is probably 67. Okay? So now letter E says, would you characterize the relationship between the low and high temperature as positive correlation or negative correlation? This is probably a phrase that you've not heard before. So let's define it right here. So a positive correlation exists when the 2 variables move in the same direction. So do you see how the low temperatures were increasing here? So the low temperatures were getting bigger and bigger, and then so were the high temperatures. So that low temperatures are increasing and the high temperatures are also increasing. So this becomes a positive correlation. They both go in the same direction. Okay? A negative correlation is when one variable moves in, and when the variables move in different directions. Okay? So, and we're going to see that in the future. But a negative correlation exists when the 2 variables move in opposite directions. When 2 variables move in opposite directions. Okay, so something like this would be a negative. This is a negative correlation. So it's very similar to negative and positive slope, except correlation is going to be talking about context. So something has a positive correlation when we talk about the real things. So as low temperatures increase, high temperatures increase. If it were a negative correlation, it would say as low temperatures increase, high temperatures decrease. Okay, that would be a negative when they do the opposite. Okay, so there's something really important in statistics that happen when 2 things have a very strong relationship, like they both increasing, but they aren't increasing because of each other. So we're going to talk about something in this lesson called a causal relationship. So two variables can have a strong relationship with one another, as seen on that scatter plot we just did, where low temperatures and high temperatures both increase together, but might not have a causal relationship. So let's read this. This is really important when I'm putting a star next to. A causal relationship exists when the change in one variable actually causes the change in the other. So we can say that, you know, the more I eat, the fatter I get. I'm getting fat because I'm eating more, right? Those two things are related. One is causing the other. But what if happened if I said something like, the more I eat, the taller I get, right? There might be an instance where a tall person eats more, but it's not that they're getting tall because they're eating more, right? So we're going to talk about examples of this in exercise 2. So exercise 2 says, in each of the following scenarios, two variables are given that if plotted would have a strong correlation, meaning the data would fall in a line. It'd be either an increasing relationship or a decreasing relationship. Determine if there exists a causal relationship between the two variables, and if so, which one causes the other. So let's look at exercise A. The high temperature in New York City and the number of water bottles sold. So you're going to ask yourself, well, is one of these things causing the other? If the temperatures in New York City get higher, are the number of water bottles selling going to get higher? Most likely yes, actually, because when it gets hot outside, what do people get? They get thirsty, right? So as it gets hotter, people want to drink more. People get thirsty, so they buy more water. The heat causes people to buy water. That is a causal relationship, right? One variable is causing the other to happen, okay? And that would look like, this graph would look like this. As the temperatures get higher, the water bottle sales get higher. So this would look like a positive correlation, okay? Letter B, a person's height and a person's shoe size. So let's think, does a tall person cause their shoe size to get bigger? So as they get taller, is the height causing their feet to get bigger? It might be a pattern that a taller person is likely to have a larger shoe size, but I don't think that one is causing the other. I don't think that your height is causing your feet to get bigger, right? It's genetics. Your shoe size, how big your feet are and how tall you get is predetermined in your DNA. One is not causing the other. Okay, so this is not a causal relationship. Now, it could look like this in the graph where, the person's height, as a person gets taller, their shoe size is bigger, so it might look like this. Really tall people have big feet usually, but it's not the cause between them. Okay, so this one is not a causal relationship. Letter C, a person's weight loss and the number of hours a person spends in the gym. So is someone's weight loss dependent on how much time they spend in their gym? In other words, is the weight loss caused by them exercising? Yes, absolutely. When you exercise, you're going to lose weight because you're exercising. So yes, weight loss is a cause. Oh, wait, I'll write it this way. Weight loss is happening because, notice the word cause is in because you are working out. Okay, so again, this would also be a correlate. If you're going to the gym, you increase your hours of the gym, you're going to increase your weight loss. Okay. And the last one, the years an education a person receives and the salary that person starts upon entering the workforce. This one's, to me, pretty obvious. The longer you're in college, will you get paid more because of college? Yes. The more education you have, the more money you will earn, which is the main reason most of us want to go to college, is so we can make money. So yes, the more years you go to college, the more money you make. Well, or you should. Not always guaranteed, but the idea is that you should make more money the more years you go to college. One causes the other. Okay, so when you're thinking of a causal relationship, think of it like this. Does one thing happen because, you can use the word because, if you like the other better because of the other. And this requires critical thinking skills. Really, exercise 2, there's no real math. This is are the two variables related? You have to really think about the situation. Okay, there's no calculating, there's no need to write a formula. You're really just having some critical thinking skills with this kind of statistics. Okay. There are also variables that have extremely strong correlations but no causal relationship, meaning that there are two things look like they're both increasing together, but they're not actually the cause of each other. And there's actually a really cool website that shows interesting correlations but no relationship. Example 3 shows this a little bit, and sometimes this happens because of something we call a lurking variable, where something else is going on in the data that we're not really thinking about, but it's causing a relationship. So exercise 3 says the table below shows the number of firefighters required to fight a given fire versus the dollar damage done to the house by the fire. So that sounds really complicated, so let's sum up that a little bit easier. So in this table we have the number of firefighters right here. So 2, 3, 5, 8, so there's the number of firefighters. And the other piece of data is the damage done by the fire in dollar amount. So when there were 2 firefighters fighting this fire, the damage dealt was around $3,000. When there's 3 firefighters fighting, the damage went up to $10,000. When there was 5 firefighters, it went up to $15,000. So what is happening here? It seems to me like the more firefighters fighting a fire, the more damage is being done to the building, which is kind of strange. You'd think that, oh, there's more firefighters fighting the fire. Let's see how many times I can say the word firefighter in one sentence. But if there are more firefighters, there shouldn't be more damage, right? If you've got more firefighters, they should be putting the fire out. So what's happening here? Well, first of all, is this data positively or negatively correlated? This data is definitely positively correlated. I can tell that because both variables are increasing. Okay? They're both going up. Firefighters are going up and the damage is going up. So this is a positive correlation, and I can tell because they're both increasing. Okay? And B, we have to think about this. Does the number of firefighters cause the damage done to the house? Meaning, if I call 2 firefighters to put out my fire, will that do less damage than if I call 10 firefighters to fight my fire? Well, no, not in real life. If I have more firefighters, I should be putting the fire out. So what's happening to this situation right here? What's actually going on? There's something called a lurking variable here. Okay, and the lurking variable is the fact that the size of the fire is not taken into account here, right? The size of the fire. The larger the fire, hold on, let me rewrite that. The larger the fire, why can't I type? The larger the fire, the more firefighters are needed. And the bigger the fire, it's going to do more damage. So what are we not thinking about here? We're not thinking about the size of the fire. A bigger fire will do more damage. Okay, so there really should be a third box here that says the fire size. There really should be, because we're making assumptions about firefighters. We're saying that, look, if we've got a lot of firefighters, your fire is going to be really bad. And that's not exactly what's true, right? We're not thinking about the size of the fire. So when you're thinking about statistics, you really have to think about all the variables going on, which is honestly why statistics can be hard, because there's a lot of things we don't know going into data. Okay, so this lesson was kind of a critical thinking lesson. You're taking away positive and negative correlation. So that was one of your aims. Can you tell if something is positively or negatively correlated? Can you find lurking variables in the data? Can you think of, well, something's not right here, there's something we're not thinking about at the data? And can you walk away thinking about whether one variable causes another variable? Okay, so that's what you're taking away from lesson 10.3, and your fluency is going to help you think through these problems a little bit more. Okay, good luck.